This is a Minecraft roller coaster. Now, it may not be the most extravagant, but it features a 100 block drop at a 45-degree angle and a hill right after, also at a 45. If I were to start at rest at the top of the drop, how far up the hill do you think I should go? Well, spoiler alert, because Minecraft rails are the most inefficient mode of transport ever made. And to know why, we first had to find Minecraft's gravity, which is much different than Earth. And to do that, we first have to know how massive a Minecraft world is. It's well known that a block in Minecraft is a cubic meter. The world, 60 million by 60 million blocks, making the surface area of a Minecraft world 3.6 billion kilometers squared, 7 times larger than the surface of Earth. Using the area, we can find the radius and volume of a theoretical Minecraft planet. Using this equation, we can find the radius of our planet at 16,925.68 kilometers, and the volume as 20 sextillion 300 quintillion meters cubed. Now here's how big that number is. The Earth is only a measly 1 sextillion meters cubed. God, only one! This makes our planet Minecraft 18.7 times bigger than the Earth in volume. We assume the density of a dry, rocky Minecraft world was 6,750 kilograms per meter cubed, a little more than the water-covered Earth's 5,510 kilograms per meter cubed. We can find the mass of an average Minecraft world to be about 137 septillion kilograms, which is coincidentally almost the exact same mass as Neptune. Now that we know the size and mass of planet Minecraft, we can use this equation to find its gravity. Force of gravity that will be acting constantly on the player. So substituting the radius and mass of the world, gravity comes out to be, wait, what is this big G thingy looking thing here? Why is there a big G?
Hello viewers, let me introduce you to Newton's law of universal gravitation. This law tracks every other mass proportional to the square distance between them.
Okay, but no one cares. Big G is basically a number that explains gravity with proportion to mass and volume, and it equals this number, which is very, very small. Plugging all this in, we get our acceleration of gravity at 31.4232 meters per second squared, which is 3 times Earth's gravity, which should kill you by sheer pressure, but you know, let's assume that you somehow survive being compressed by celestial forces. 3 G's of force is about what you feel when you're upside down in a loop-de-loop, meaning our numbers will look extraordinarily large. Our drop has a height of 100 meters and a length of 117 meters. And we can find the mass of our minecart plus rider by taking the average weight of a cubic meter of iron and then divide it, multiply it, and then add around 60 kilograms to get a total mass of 4,393.3 kilograms, which is the mass of an entire roller coaster train in just one cart. Now, to know how fast the cart accelerates, we'll take our gravity value rounded up to 32 and divide it by sine 45 to get our cart's acceleration down the drop of 45 meters per second squared. Using this kinematic equation and subbing in our values, the velocity of the cart at the bottom of the drop is a breakneck 103 meters per second. Now, to know how far up the hill our basically now rocket cart can go, we can use the law of conservation of energy that tells us that the energy going in is equal to the energy coming out. By using this formula, which is derived from kinetic energy down here and the gravitational energy up here, we'll first substitute our known values, 103 meters per second and 32 meters per second squared, giving us a final height of 166.2 meters. So to find the distance traveled up the hill, we have to find the hypotenuse between points 2 and 3. And we can just do good old Pythagorean theorem for this, giving us a total length of 235.04 meters up the coaster before coming to rest. But what these numbers tell us is that there has to be another force involved, because by doing a simulation of our coaster, we can see that the cart travels a mere 32 meters. Not to mention that it's not possible for the cart to go higher than the drop it started from. So there aren't many options left when it comes to other forces involved, and it's pretty clear that when we did these calculations, we did them assuming there was no friction. So let's find our friction. Adding thermal energy to our equation and rearranging for Fk and using this stopwatch to find any other missing values, the force of friction on this roller coaster comes to a whopping 92,708 newtons, which across the entire track is probably enough thermal energy to melt the cart and the rider inside of it.